Hello and welcome, hopefully welcome back to the next in OpenEye Cadence Molecular Sciences series of webinars on computational drug discovery. My name's Paul Hawkins, Principal Product Evangelist here at OECMS, and I shall be your host for today's presentation. I'm delighted to welcome as our speaker today Dr. Greg Bakken, head of our Hit ID and Small Molecule Solution Vertical. Greg's title today, Improving the Core, Not Resting on Our Laurels. Greg came to us from an over 20-year career at Pfizer, where he worked both in project support, drug discovery, and in internal software development teams. So in the course of that time, Greg's touched almost every aspect of small molecule design. So I'm very much looking forward to what he has to say today. If in the course of Greg's presentation you have any questions you'd like to pose, please put them in the chat window of the interface, and we shall try to answer them at the end of the presentation. If we do not get to your question in that time, we shall try to answer it by email as soon as possible. The webinar is over. So with that housekeeping note out of the way, Greg, over to you.
Thanks for the introduction, Paul, and thanks to everyone online for joining us today. As Paul mentioned, I lead the Hit ID and Small Molecule Design group, and we're responsible for a lot of the foundational tools that OpenEye has built over the last 25 plus years. And while OpenEye has built many new and exciting things since then, we've also continued to focus on those core tools to ensure that they remain state of the art. And what I'm going to talk to you about today is some of the work that we've had going into one of the most important of our core tools, Omega, our conformer generation tool. So why do we care about conformation generation at all? So obviously, most computational work in small molecule discovery requires us to try to find the bioactive conformation. That is, how is the small molecule going to be in conformational space when it interacts with a protein? And Omega is a leading tool in the industry for doing this. So anything we can do to make that faster and less costly while still maintaining an appropriate level of accuracy benefits our customers in a lot of their workflows. And so we're going to talk about some of the work we've done today to make improvements with Omega, and then look at how it is in terms of speed and accuracy based on those improvements. So we'll start with just a quick review of Omega. I think many people are familiar with it and have seen how it works and know some of the internals. And then we'll talk about our initial implementation of Thompson Sampling. And then we'll go into an optimized version of Thompson Sampling and really look in more detail at speed and accuracy of Omega. If you've seen many talks from OpenEye, you've seen a slide that looks like this. So this shows our array of toolkits broken apart as those that support molecular modeling efforts and those that support cheminformatics efforts, with OEChem sort of as the linchpin that joins the two. I think on the molecular modeling side, it might be more accurate to think about it like this, with Omega as the foundation. Omega conformer generation supports many of the other toolkits and workflows that our tools support, and so any improvement we can make in Omega is going to benefit many other things. There's two modes of conformation generation in Omega, the first being for small molecules. So here we take a torsion driving approach, and this is what I'm going to spend most of my time talking about today. But for macrocycles, we use the distance geometry-based approach, so a slightly different path. But as I said, I'm going to spend most of my time today talking about torsion driving. So how do we build conformations with Omega? So we start with a small molecule, and what we need first are some initial 3D representations. So we generate one or more structures in 3D using a fragment library that helps us sort of define templates for what ring systems and things might look like. And from there, we identify rotatable bonds. And we map those rotatable bonds to our torsion library, which provides us the most likely torsions for each of those rotatable bonds. Then we look at the combinatorial expansion of all of those rotatable bonds and all of the possible torsions for those rotatable bonds to generate a sometimes very large conformational ensemble. And then we have to think about which of those conformations do we want to keep in the final ensemble. So we want to slice that ensemble and choose which conformations we think are most important to keep. And that's going to depend on the application for which you're generating the ensemble. So there are a series of hyperparameters available, looking at energy windows, the maximum number of conformers you want, how similar the conformations are. And the user can control this to dictate what sort of ensemble they're going to generate. And this is really our exhaustive sampling approach. This is how Omega was originally designed and how it's been built up over the years. While the user gets fine-tuned control over the hyperparameters to do ensemble slicing, we also have some convenience modes in Omega. These modes essentially set hyperparameters that are very consistently used with particular applications. For example, if you're going to generate conformational ensembles for FastROCS searches, you can use FastROCS mode, which will set the hyperparameters for ensemble slicing to generate conformational ensembles appropriate for that application, where maybe you only need 10 or so conformations. If you are doing something like crystal structure prediction, you may want a lot more conformation, so you might want to use something like dense mode. So these are set up for convenience for users, but again, the user has full control over all of those parameters if they want to define a conformational ensemble in their own way. So that's just a quick overview of Omega, as I said. And now I want to talk a little bit about an initial version of Thompson sampling that we've implemented. So Thompson sampling is fairly well known. It's been used in several areas of drug discovery. So I'm not going to spend a great deal of time talking about Thompson sampling in general, but I do want to talk about where we're using it in Omega. So the idea here is we want to try to speed up that torsion driving process. So what we do is we start with our structure and we identify all the rotatable bonds, just as we did before, and we map those to our torsion library to see which angles are most likely to occur for those particular torsions. Now, in exhaustive sampling, what we do, as I mentioned, is we look at that full exhaustive space, so the full combinatorial set of conformations we can generate. But with Thompson sampling, we want to try to avoid that. We want to try to sample that space. So we think about priors for each of those torsion angles, and then we can sample from those. So this is sort of that classic multi-arm bandit view where we pick a particular torsional angle for each of the rotatable bonds, and we use that to generate a conformation, which we can then assess and score. And we can continue to repeat this process and each time we generate a new conformation, we look at the characteristics of that conformation and is it good or bad? And good or bad might be defined based on the strain of the conformation, how unique it is relative to the rest of the ensemble, etc. And based on that information, we update the probabilities for the priors for each of those torsional angles. So what we're trying to do is drive to using the torsional angles that are giving us the best conformations. One of the key questions when we do this is how much sampling should we do? So the key is to balance, are we exploring new conformational space with whether we've seen torsional angles that are giving us conformations of interest and we want to continue to exploit that information. And we found, similar to the modes that we set for Omega, that we have heuristics parameters, if you will, that tell us how many trials we need to do for each of those modes. So if we're doing small ensembles, we can do fewer trials. If we're going to do larger ensembles, we want to do more trials. And so here you can see we have a table that just shows the amount of sampling we do relative to the number of rotatable bonds for each of the modes of Omega that we're going to run. So as we evaluate whether our changes to use Thompson sampling are effective or not, as I mentioned previously, we want to think about speed and accuracy. So we're going to look a little bit first at speed, but we'll also look at accuracy and how well this performs in actual virtual screening exercises. And we're going to focus on two particular modes, FastROCS, where we're generating ensembles with a maximum of 10 conformations, and classic mode, where we're generating ensembles with a maximum of 200 conformations. So to start with, we're going to think about speed, and we're going to do this by looking at the initial implementation of Thompson sampling, and we're going to look only at the set of 6,000 compounds from the PDB. So these are 6,000 ligand co-crystal structures. Later on, when we look at speed in our optimized version of Thompson sampling, we'll also consider randomly selected sets of 10,000 compounds from both enamine and Schurkenbel, as well as 13,000 drug-like molecules from a set from GSK. So this is a plot looking at the speed of conformational ensemble generation for FastROCS mode. So on the y-axis, we have the time for conformational ensemble generation in seconds. And on the x-axis, we have the number of rotatable bonds in the structure. So here we're comparing exhaustive sampling with our initial implementation of Thompson sampling. And what we can see is with Thompson sampling, we're generating our ensembles in less time, and there's not significant variability in time among compounds with the same number of rotatable bonds. So we're getting nice tight bands there. Now, if we look at the time axis on the y-axis, you might say this isn't significant. This isn't significant savings. And you're right. If you were generating a conformational ensemble for a single structure and you could save a tenth of a second, that probably wouldn't be significant in your workflow and you really wouldn't notice it. However, if you can save a tenth of a second per ensemble and you're generating conformations for 1 billion compounds, that's a savings of about 1,200 CPU days. So it is very significant when we start thinking about larger and larger sets of compounds. And as I mentioned, omega is foundational to so many of our workflows. We're doing conformer generation so frequently that even small savings like this is very beneficial. Another way to look at this same data is just by making the y-axis a delta of time. So we're taking the Thompson sampling time and subtracting from it the exhaustive sampling time. And so we see that we see a consistent decrease in the average time for ensemble generation throughout the different numbers of rotatable bonds. And we see we save more and more as we go to larger numbers of rotatable bonds. So for FastROCS mode, we're pretty happy with this. We see a nice, consistent improvement in time for generating these ensembles. So if we then want to extend that to classic mode, we see something somewhat similar, but not quite as good. So we're still seeing an improvement in time to generate ensembles, but it's not as consistent, particularly when we get to larger numbers of rotatable bonds. And there's much more variability at a particular number of rotatable bonds, particularly as we get to the larger numbers of rotors. And we see the same thing here if we look at this as a delta plot. We see that we get time savings overall, but it's not as consistent as we would like it to be, and it's not as significant as we would like it to be. So we were pretty happy with this implementation. We saw improvements, particularly for FastROCS, but we didn't see the improvements we would like to see for larger ensemble sizes. And so we thought about what else could we do to this? And a lot of this went back to all of the time and effort that's been put into Omega over the years and optimizations that we found as we've improved the exhaustive sampling approach. And we thought about how we could bring those to bear on our Thompson sampling approach. And so this led us to the optimized version of Thompson sampling that I'm now going to talk a little bit more about. So we'll start with a plot that looks very similar to what we looked at with the initial Thompson sampling implementation, where we're looking at conformational ensembles generated in FastROCS mode. And we see that relative to exhaustive sampling, this new version of Thompson sampling is giving us significant improvements in time per ensemble generation, and it's very consistent from compound to compound with the same number of rotors. More specifically, we see an overall average speed up of about 3x. So it's a little bit more of a speed up with the larger compounds, a little bit less with some of the smaller compounds that tend to have smaller conformational space to sample from because there are fewer rotors. If we look at a delta plot here, now we can compare easily the optimized version of Thompson sampling and the initial version of Thompson sampling. And what we see is they both behave quite similarly. They both show consistent improvement in time for generating ensembles. And you can see that the optimized version of Thompson sampling is maybe a little bit better than the initial implementation in FastROCS mode, but fairly similar. And so now the question is, does this optimized version work well in classic mode? And we can see here that it actually does work quite well in classic mode as well. So we see a much more consistent decrease in time as we go from, as we look across number of rotatable bonds. And as we get to the larger number of rotors, we see that our time windows for ensemble generation are staying nice and tight. And overall, we see in classic mode about a 2x speed up here. And again, we see a little bit more of a speed up with the larger number of rotatable bonds than the smaller number of rotatable bonds. And really telling is if we look at the delta plot here and we compare the initial version of Thompson sampling with our optimized version, you can see particularly towards the right of this plot that we're doing a much better job with those systems with a larger number of rotors, and we're getting a consistent decrease in time, whereas with the initial implementation of Thompson sampling, we were not. So one of the things we did wonder about is whether we should be looking at this relative to the number of rotatable bonds, or if there was a different way we should think about molecular flexibility. So each rotatable bond is not necessarily created equal. Some rotatable bonds have only two particular torsions from the torsion library that they're likely to exist at, while other rotatable bonds might have 8 or 10 or 12, or even more. And so one of the things we wanted to check was, would it make a difference, would our conclusions change if we thought about molecular flexibility differently? So what we're looking at here is, for the same set of compounds, we're looking at the number of rotatable bonds on the x-axis and the overall size of the torsional space. So if we multiply the total number of torsional angles for each rotatable bond together to get the full size of the conformational space to consider, that's on the y-axis. And we see right away that there's a pretty reasonable linear relationship here. So it isn't surprising that if we change the x-axis from number of rotatable bonds to simply size of the torsion space, that we still see the same trends we were seeing before. We're getting decreases across the board with the new version of Thompson sampling, and the windows for time for conformational ensemble generation with this new version of Thompson sampling are staying nice and tight. So this just increases our confidence that looking at the data based on the number of rotatable bonds isn't somehow misleading us in some way. Okay, so we're pretty happy with the speed ups we're seeing with Thompson sampling, and it's great that we can generate these ensembles faster, but we haven't done anything yet to convince ourselves that these are good conformational ensembles. And so we want to look a little bit at accuracy. And so one of the important ways we can assess accuracy is whether the ensembles have the bioactive conformation present somewhere in the ensemble. And to do that, we extracted 6,000 co-crystal structures from the PDB. And here we were looking at those that were deemed highly trustworthy by Iridium. So a lot of work went into developing Iridium scoring by Greg Warren and coworkers. And this really assesses co-crystal structures, and it buckets them into three categories: highly trustworthy, medium trustworthy, and not trustworthy. And this is telling you in a glance about whether or not this crystal structure has good density information and things like that. And so what we did is we limited ourselves to highly trustworthy structures, and we also filtered by molecular weight and heavy atom count. And this left us with about 6,000 structures for which we wanted to see if we were generating the bioactive conformation for the ligand. So for each of the 6,000, we generated conformations using exhaustive sampling and using Thompson sampling, so two separate conformational ensembles. And then for each, we wanted to see if any of the conformers in the ensemble was close to the bioactive conformation. So here's a plot that provides this information. So this is looking at, on the x-axis, the RMSD. So this is the conformer from an ensemble that's closest to the bioactive conformation. And the RMSD is telling us how far apart they are. And on the y-axis is telling us the percentage of molecules that are at or below each RMSD value. So 80% of the molecules are within 1 angstrom RMSD of the bioactive conformation. This plot also shows us that Thompson sampling and exhaustive sampling are behaving virtually exactly the same. There's no difference in those two lines. And so overall, we know that we're getting conformational ensembles from Thompson sampling that have overall the same accuracy as exhaustive sampling. We can dig into this a bit more and look at specific cases. So we can do a pairwise comparison of all of those structures, and we can look at the RMSD for Thompson sampling relative to the RMSD for exhaustive sampling. And we can see here that in about 93% of the cases, the RMSD of the conformer from the ensemble that's closest to the bioactive conformation these are within about a quarter angstrom plus or minus. There's a few cases where Thompson sampling's a little worse, a few cases where Thompson sampling's a little better, but overall we're seeing very consistent behavior in the ensembles generated with Thompson sampling. One final way we can look at the same data is by number of rotatable bonds. So here we can see two things pretty quickly. One is not a surprise, right? The larger the number of rotatable bonds, the higher the RMS to the bioactive conformation. And this isn't a surprise. The more rotors you have, generally speaking, the harder the problem is going to be to find that conformational ensemble. There's more flexibility in the molecule. But the other thing we see very quickly is that exhaustive sampling and Thompson sampling ensembles are behaving very, very similarly. And so, again, this is reassuring. This is telling us that we're generating ensembles with Thompson sampling that are very much equivalent to what we were getting from Thompson sampling. Okay, so we've established we can build these ensembles faster. We've looked at the ability to regenerate bioactive conformers somewhere in the ensemble. Now we want to take a look at how well these do in a virtual screening application. And so here we're going to use a literature publication where 43 targets from DUDZ were examined. So for each of these targets, there were a set of active compounds and then a set of decoys that were present in about a 1 to 50 proportion, actives to decoys. So this is the sort of classic experiment where we want to see how well we can do in ranking those active compounds. So we take the compounds, both actives and decoys, generate conformational ensembles, either with exhaustive sampling or Thompson sampling, and then we did our docking with Fred. And we rank the compounds based on the ChemGauss4 scores from Fred, and then we can calculate AUCs. So an AUC is telling us how well are we doing at getting the rank orders correctly. Are we getting those active compounds at the top of the list if we were to select based on these docking scores? And what we can see here across the 43 targets is there's no difference in the average AUC value between Thompson sampling and exhaustive sampling. And if we look at the plot that's comparing the values, we can see that the majority of the points are right on that parity line. And if we look at the 43 targets individually, we can see towards the top, we have some targets where Thompson sampling is doing a little better. And toward the bottom, we have some targets where exhaustive sampling is doing a little better. But if we look at the magnitude of the changes on the x-axis, they're pretty small. These are very close to each other. So across the set of 43 targets, we can say that we have a lot of confidence that Thompson sampling is behaving equivalently to exhaustive sampling. But we may also want to dig into some of these targets and just make sure we understand exactly what's going on there. And so if we look at one of them, ABLE1 specifically, we can dig in and say, okay, so what were the ranks from ChemGauss4? So we do our docking, we rank our compounds to calculate the AUC. What did those ranks look like? So here on the y-axis, we have the ChemGauss4 rank using Thompson sampling, and on the y-axis is the rank using exhaustive sampling. And in the plot, the blue dots are the decoys and the green triangles are the active compounds. So what we want to get the best AUC possible is we want as many of those green dots at the beginning of this list towards the origin as possible. And we can see here that the green dots, there's a slight prevalence of green dots below the line versus above the line. And this tells us that Thompson sampling did a little bit better with the ranking than exhaustive sampling. And that's why the AUC improves slightly for Thompson sampling. So we can look at this plot and we can tell that Thompson sampling did a good job in terms of generating conformational ensembles that gave us similar ranks based on ChemGauss4 scores. And we can take this a step further and we can say, well, let's compare the actual ChemGauss4 scores. And that's what we have on the right here is the ChemGauss4 scores out of Fred for Thompson sampling on the y-axis, exhaustive sampling on the x-axis. And we can see again that for both decoys and actives, we're getting very consistent scoring. And we can see again that we get slightly more negative scores. And keep in mind, the more negative the score coming out of, the more negative the ChemGauss4 score, the higher rank the compound will be. And we can see that the active compounds have slightly more negative scores for Thompson sampling. And again, this explains why we saw a slight improvement in AUC value. All right, so to wrap up, what have we learned today? Well, we've seen that omega with Thompson sampling is giving us a speed up, specifically about 3x with FastROCS mode and about 2x in classic mode. So if we think about what that really translates to, if we just look at strictly the compute time for conformer generation for 5 million molecules, and we think about doing this in Orion, this is roughly equivalent to about 15 minutes, and it's going to cost us a little bit under $6. So 5 million compounds is probably about the size of many corporate collections. And so you can generate conformations for that in about 15 minutes. If you're looking at larger sets, say a billion compounds, you can do that in about an hour. It's going to cost about $600. So that's just to give you an idea of what it's going to take for conformation generation cost-wise. We verified that we're actually getting good ensembles out. And we did this in two ways. The first is we confirmed that our ability to predict bioactive conformations is really unaltered. We still get 80% of the ligands within about 1 angstrom RMSD, similar to exhaustive sampling. And we also looked at an application in structure-based design where we used 43 targets and found that the AUC values across those 43 were indistinguishable between exhaustive sampling and Thompson sampling. Some other things we're thinking about and want to let you know about. The first is in our summer toolkit release, Thompson sampling with omega will become the default, and our toolkit and application release. So starting in the summer, this will become the default mode for which we do conformer generation with omega. We're also looking at doing some additional work. So we're very happy with how Thompson sampling has shown us some improvements in omega, and we want to see how far we can stretch that. So we want to look at things like peptides and cyclic peptides and macrocycles and see if we can find ways to improve conformer generation for those larger structures as well. We'll also be moving to, in the Orion world, doing FastROCS only collections for large-scale virtual screening. So for those of you that screen the vendor libraries on Orion, we're going to start doing generation of only FastROCS collections of those vendor libraries using Thompson sampling. And so when we run Gigadoc Warp, we'll do conformer generation on the fly. So we won't have to generate the full conformational ensemble for all of the compounds in those large libraries. So that'll save some time and size and data movement in Orion for screening those collections as well. So I want to close with a quote. This is from Bruce Lee, and he said, "I fear not the man who has practiced 10,000 kicks once, but I fear the man who has practiced one kick 10,000 times." And I think that's really relevant here. Omega is a tool that OpenEye has worked on for a number of years, and it has been state-of-the-art in small molecule conformation generation. And it's something that we're continuing to improve and will continue to improve in the future as well. So in closing, I want to thank Radish and Shumal in particular. So they did the majority of the work that was presented today. And also Caitlin and Jeff for discussions about different things we might want to do in Omega to further improve it. And with that, I'll thank all of you for your time and attention, and I'm happy to take any questions.
Thanks, Greg. Magisterial as always. We've had a few questions come in over the course of the talk, so I'll warm you up with one. You contrast the exhaustive versus Thompson sampling case, and pretty much Thompson sampling seems to win every time. Is there a case that you have found or that you could foresee where what we call traditional exhaustive sampling would be a better choice than Thompson sampling?
Sure. So I think depending on your application, if you want to look at a very dense ensemble of conformations, then exhaustive sampling would be the way to go. So if you're going to do something like crystal structure prediction, where when you want virtually every bit of conformational space covered, it makes more sense to do exhaustive sampling because it will simply just take longer for Thompson sampling to cover that same space.
Right. Okay. So you're looking for an exhaustive or a dense. That does what it says on the tin, I suppose, exhaustive sampling. So you've made I think, a very good illustration of how accurate this is, and you've got that really nice plot of the accuracies from exhaustive sampling versus Thompson sampling. Given that exhaustive sampling is, by its nature, exploring all possible angles we could think of for a given set of torsions, how is it that Thompson sampling ends up with a more accurate reproduction of a crystal structure than exhaustive?
Sure. And so that comes down to the step of ensemble slicing. So you're right. In the exhaustive sampling approach, we would be considering all of the same conformations that Thompson sampling could be considering. And then it's simply a matter of which of those get selected for the final ensemble. And so in Thompson sampling, what we're finding is in a few cases, we do see a more optimal conformer selected in that final ensemble than we get with exhaustive sampling.
Okay, so it really is down to the energy function, nothing to do with a superiority of the two sampling methods.
Correct.
Yeah, very good. And then excitingly that you sort of closed with this note that we will now be changing the way we use our ML-enabled docking engine, Gigadock Warp, and particularly it's going to have an effect on cost. Do you have some guesstimations for what the impact on Thompson sampling for on-the-fly generation of conformations for docking is going to be?
Yeah, so clearly, doing the on-the-fly conformer generation is going to cost a little bit as part of the Gigadock Warp run. But keep in mind, with Gigadock Warp, we're docking a small fraction of the overall set of the compounds. So it won't be a large number of compounds for which we have to do the conformer generation for docking. So a little bit of cost to do the conformer generation, but we're avoiding a significant cost because we don't have to move around large databases of conformers. So normally with Gigadock Warp, we have pre-generated large ensembles of conformers to use with docking, but we have to move those around in AWS. And we won't have to do that step anymore. And that proves to be pretty costly. So we're actually hoping that we won't see a significant difference in the overall cost of Gigadock Warp. It will just be where we're spending the resource. But the overall cost we're hoping stays fairly similar.
Right. And we will in the long term, everybody will in the long term save the storage costs too.
Correct.
Yeah, very
Yep.
good. Thanks, Greg. That's all we had time for here. So that's the end of the Q&A.
All right. Thank you. And thanks everybody for attending.
So thank you all very much for attending. I hope you found the webinar today as entertaining and as informative as I did. That brings today's webinar to a close. I look forward very much to seeing you at the next one. So until then, goodbye.